Welcome back again for Advanced Functions, MHF4U 1. This is still under the Rates of Change lesson. We're going to take a look at lesson number 4, which is applying the word problems involving rate of change. So our learning goal today is to take a look at a variety of word problems in an application setting where we can find the instantaneous rate of change and average rate of change. First of all, let's do a recap of instantaneous rate of change. Now, there are two methods. Method number 1, we said that we could use as h approaching 0, so limiting so that h is going near almost at 0. And the second method is by letting h is equal to, you could do plus or minus 0.01. Now, if you're limiting so that h is approaching 0, there are three equations that you could apply and it will work really well. So the first one will be any type of polynomial equation. You would say let h approaching 0. Also, you could apply this method for a rational function and a square root function. Okay. Now, on the other hand, if you come across any logarithm function, exponential, trigonometry, absolute function, or it could be polynomial, but if the coefficient is irrational, then I would recommend you to let h is equal to 0.01. Okay. So question number 1, determine the instantaneous rate of change for the function at x is equal to 2. So this is, first of all, identify this is a polynomial function. So I could do instantaneous rate of change is equal to f at a plus h minus f at a over h, so that h is approaching 0. So we can plug in the a value, which is 2 plus h minus f at 2 over h. So I will be doing the side work for the calculation. So on the side, I will be doing f at 2 plus h into, so you will be plugging 2 plus h into x. So therefore, it will look like 3, 2 plus h squared minus 7, 2 plus h plus 5. So you will be expanding. So 3, 4 plus 4h plus h squared. And then you'll be doing distributive property, negative 14 minus 7h plus 5. And then you will continue to do the distributive property. So in the end, you'll be left with 3h squared plus 12h plus 12 minus 14 minus 7h plus 5. So I'll be collecting the like terms. So 3h squared plus 5h plus 3. Okay, so this is my output when it's 2 plus h as an input. And then we also have to do input the function when it's 2. So I'll be plugging in 2 into x. So 3, 2 squared minus 7, 2 plus 5. When you evaluate it all together, you should be getting 3. Okay, so now we are going to plug in the information. So h approaching 0, and then 3h squared plus 5h plus 3. So that is for 2 plus h output. And then for f at 2 output will be minus 3. Okay, and then h. So you will notice that this cancels out. Okay, and then you also notice that h could also cancel out. 1, 1, and 1. Okay, so therefore, h approaching 0, you'll be left with 3h plus 5. Now, as soon as you cancel the denominator of h, now we can plug in h as 0 because it will no longer be undefined. So when we are plugging in h, you no longer write h approaching 0 because we're plugging in now. So 3 times 0 plus 5. So therefore, the instantaneous rate of change is 5, which is the most exact answer. Instantaneous rate of change. Okay. Number 2, a company's profit in millions of dollars, so the unit is in millions, is modeled by the function where n is the number of units sold in thousands, so you have to be careful with the units, and show that the maximum profit occurs when 2,500 units are sold. Now, maximum profit. So as soon as you see maximum or minimum, it means that the slope of a tangent line must be 0, because maximum happens when the tangent is 0, and the minimum happens also when it's 0 as well. So the instantaneous rate of change at maximum must be 0. So we need to prove that it's 0 when n is equal to, so the units is in thousands, so it must be 2.5 units, because it's 2,500 and the unit is in thousands. So let's write down instantaneous rate of change is equal to, so because it's polynomial, I will be saying as h approaches 0, and the profit, so we know a is going to be 2.5 plus h minus profit at 2.5 over h. Okay. Now you're going to do the side work again. So on the side, I will be doing profit 2.5 plus h. So I will be plugging this into my n value over here. So it's going to be negative 3.5, 2.5 plus h squared plus 17.5, 2.5 plus h plus 10.125. Okay, so now you're going to do a FOIL again, same thing. So negative 3.5. So if I do the FOIL, so it's going to be h squared plus 5h plus 6.25. And then you're going to do the distributive property here. So plus 43.75 plus 17.5h plus 10.125. Okay. Lastly, you're going to do the distributive property, and then you are going to collect the like terms. So once you collect the like terms after distributing property, you'll get negative 3.5 h squared plus 32. Okay, that is my output. We also have to figure out what the profit is when it's at 2.5. So again, I'm plugging in 2.5 into all of my n. 2.5 squared plus 17.5, 2.5 plus 10.125. And after you evaluate everything, you should be getting 32. Okay, we can now plug in all the output into the equation. So I'm just going to move to the side. So h approaching 0. So the output for this one, it's going to be negative 3.5 h squared plus 32. And then minus at 2.5, it's going to be 32 as well, over h. Now you will notice that 32 and 32 cancels out. 32 minus 32 is 0. And then you will also notice h approaching 0 is that negative 3.5 h squared over h. So you will also notice that h and h cancels out. So therefore, h approaching 0 is going to be negative 3.5h. Okay, so now we can finally plug in h as 0. So I no longer write h approaching 0, so negative 3.5 times 0. And what does it give me? It's 0. Okay, so we just proved it. So therefore, the instantaneous rate of change is going to be 0 when n is equal to 2,500 units sold. So in this case, I'm going to write 2.5 because it's in 1,000. So therefore, we can say that the maximum does occur. So maximum, it occurs at when they sell, occurs when they sell at when they sell 2,500 units sold. Okay, and that is my final answer. Okay, so question 3, determine the rate of change of f at x at x equals 5. Okay, so this is like any other question. It's an instantaneous because we're looking at this point. Now, the equation is an exponential. So as we learned in the previous slide, is if we get an exponential function, then the most ideal method is we have to let h is equal to 0.01. So it won't get any messy if you were to say h approaching 0. Okay, so it's the efficient way. So let's write down the formula. Instantaneous rate of change, h, so we know a is 5 plus h minus h is 5 over h. So this h, it's coming from the function h, okay, not the difference of h 0.01. So we're going to plug in 5 plus h into my variable x, so it's 3, 5 plus h, okay, minus 3 to the 5 over h. But we know what h is going to be. It's going to be 0.01. So if I were to say 5 plus 0.01, it's going to be 5.01. So it's 3 to the 5.01 minus 3 to the 5 over 0.01. So you're going to punch it in your calculator, and you're going to get about 267.12. Okay, so that is going to be my instantaneous rate of change at x is equal to 5. Okay. Lastly, question number 4. The distance of a particle in meters at time t in seconds is modeled by the function. So determine when the particle is at rest. Okay, so at rest, it means that we have to, so let me show you a graph again. So we're given a graph and it's not moving. So as you can see, at maximum or minimum, it's not moving. Okay, so therefore, if it's at rest, we say that instantaneous rate of change is going to be 0 at either the max or min. So to do that, we know, so we're going to set the rate of change to 0. So let's write down instantaneous rate of change is equal to S. We don't know what the time is. So we're going to say T plus H and then S at T over H, because that's what we're looking for. So now we can plug it in. Instantaneous rate of change is 0. And what we're going to do is we are going to plug in T plus H into my function S. So therefore, so I will be doing the side work. So S, T plus H. So we're going to plug in all of this into my T variable. So it's going to be 2T plus H cubed plus T plus H squared minus 4T plus H plus 7. So it's a lot of expanding here. So 2T plus H, and then we T squared plus 2H plus H squared. So what I'm doing right now, I just expanded the first two for the cube. Okay, and then plus, I will be doing FOIL for the next bracket. So T squared plus 2H plus H squared, 2TH, sorry. And then do the distributive property. So minus 4T minus 4H plus 7. So here you gotta do the distributive property, the FOIL, front, outside, inside, front, outside, and inside last. So all of them. So once you do FOIL and you collect the like terms, so you should be getting, it will be 2T cubed plus 6T squared H plus 6TH squared plus 2H cubic plus T squared plus 2TH plus H squared minus 4T minus 4H plus 7. So I haven't collected the like terms yet. I just expanded. Okay. And so we could put S at T. So let's plug it in. So it's going to be 2T cubed plus T squared minus 4T plus 7. Okay, so it's going to look exactly the same. So what I'm going to do now is I'm going to plug this. So collect the like terms for this and this one. Okay. So we will be subtracting this. Don't forget, when you're subtracting, make sure you put a bracket, this minus the whole thing. Okay, so it applies the distributive property. So once you apply that, you get 6t squared h plus 6th squared plus 2h cubed plus 2th plus h squared minus 4h, okay, over h. Okay. So for this case, because it's a polynomial, don't forget to write h approaching 0. H approaching 0. Okay, so now you can cancel all the h, right, with the denominator. And then 0 is equal to, so it's going to be 6t squared plus 6th, okay, because we canceled out the h, plus 2h squared plus 2t plus h minus 4. Okay, now let's apply a 0 into h, because h is now canceled in the denominator. So we're going to plug it in. 0 is equal to 0, so it's going to be 6t squared, and this becomes 0, and this becomes 0, 0. So it's going to be 2t minus 4. Okay, so now we have to solve for t. So as you can see, this is, you want to factor. There is no common factor in this case. Oh, there is a common factor. You could also, what you could do is do a trinomial. So I am going to factor 2. So 2 bracket 3t squared plus t minus 2. And then you're going to do product and sum by factoring. So 0 is equal to t plus 1, and then 3t minus 2. Okay, so now to solve for it, you're going to let each bracket equal to 0 and solve for t. So if that's the case, for the first bracket, t plus 1 equals 0, and you isolate for t, so t is equal to -1. And then for this one, t is equal to 2 over 3, once you let 3t minus 2 equals 0. Okay, now what do you notice? Is that, can the time be negative? No, the time cannot be negative. So therefore, this is not possible. So the only time that will give me when the particle is at rest is when it's at 2 over 3 in seconds. So therefore, it's at rest it's hard to write. It's at rest at 2 over 3 seconds. Okay, so make sure you double check your answer by looking at the context of the question to see if it could be negative depending on scenarios.